video. It is our pleasure to welcome Guido Sciavico from the Department of Mathematics and Computer Science of the University of Ferrara in Italy, and who has also been involved in many previous time conferences. So now we are happy to have him here to give his keynote talk that will be titled A General Logical Approach to Learning from Time Series. Please.
Thank you, Michael. Thank you, everyone, for having me here. Very happy. As he said, I've been around time for like my whole career, 22 years. I think I have never missed a single event, a single time, either as a speaker or in some other capacity. Okay, so what I'm going to talk about today is a general approach to learning from time series. This is going to be a very high level story, basically. This is the story of what I've learned about learning from time series, not just the work I've done with my group, but also the work of other people. What happens is that this work is relatively recent, so we all know each other. We almost know all each other. We work, who we work in this area. I'm going to start by a very easy observation, which is that in the past 20 years, machine learning has penetrated virtually every area of computer science. Of course, temporal learning is no exception from this. And what happens, what I'm going to show you in the first 10 minutes is just how common is temporal data in the real world. So how common is the fact that you got temporal data from your everyday problems, and then I will focus on the subfield of logical learning from time series. That is the idea of learning a logical formula from your temporal data set. And the problem is, how can we define this in a proper way so that it somehow generalizes the existing approaches? So let's focus on logical learning from time series. I divided this into three chunks. One of them is about time series and where you can find them, what I was mentioning a minute ago. So how common is temporal data? What does it mean to model temporal data set with a logical framework? And finally, how can you learn it? And I'm going to dig a little bit in the computational complexity of learning. First, we have to define the problem of what we're talking about, and then we can ask ourselves whether or not the computational complexity makes sense. It does, of course, make sense, but for which problem and what do we know about it? That's how I'm going to end this. So let's focus on time series. An incredibly basic definition. What is a time series? Time series is just a bunch of a finite number of points. To each one of them, you add a value of one of more variables. So formally, you got n points. It's a finite time series. It's a finite linear order, which we call the domain. And then we got one variable from the domain to the real numbers. If your time series have discrete values, you can model with real numbers. If you have a categorical value, you can also model with real numbers. So basically, your domain can always be the set of real numbers. And when you have many variables changing over time, then you talk about a multivariate time series. Usually, we denote with big N the number of points and small n the number of variables, just to make our notation consistent with most of the literature. Now, a temporal data set is a bunch of time series. You got n copies of this. Not copies. N instances of multivariate time series, and you put them all together in a temporal data set, and this is what you have to learn from. So the problem is how to logically describe this object. Now, as I was saying, In the past, let's say 10 years, I've been working with learning from data, and I discovered, maybe it was surprising for me, maybe it's not surprising for everyone else, just how common is temporal data. Now, each one of the examples that I'm going to present correspond to a real project in the industry that at my lab we carried on. Some of them are still ongoing. Some of them, we did them in the past. And this entire set of examples doesn't even cover all the cases that we faced during the year. So the first example is from the industry. So basically, every machine that works for a long time that works a long time can be you can put sensor on it to extract all kind of information. This is direct information, such as vibrations or gas output or the energy input. You can measure basically everything that goes on, and then you can use this for predictive maintenance or to predict events. We did this with Siemens Energy, and that is exactly a picture of a gas turbine. So basically a machine that takes the gas and burns it and produces electricity. Now the event the one they asked us to predict was the shutdown that happens sometimes in a sudden way. So of course the shutdown is electronically controlled, but the problem is that sometimes what happens is that the conditions are such that they have to shut down very quickly the machine instead of slowly decreasing the number of laps, and this stresses the machine a lot. And they wanted to know whether or not this can be predicted by looking what? By looking, as I said, the machine behaviors over time. You can find temporal data in physiology. Physiology can be defined as the science of studying the body in normal condition, not when it's sick, but when it's not sick. And there are many examples of physiology that produce temporal data. One of them is voice. Voice is basically can be transformed into a set of variable of time varying variables via Fourier-like transform. And basically, what they do is they measure how much power you put in each frequency. Now, one single event, let's say a word or a cough or a breath sample, give rise to a time series as we define. So you have many of them, and you get a temporal data set. What can you do with that? You can identify some kind of infections, for example. Actually, we just published this small example of how many different diseases you can actually classify by using just breath example and cough example, like at least 5 or 6 different infectious diseases of the lungs. But also, you can use it for other purposes, such as age and gender identification. Just a note, for gender identification, we got more than 90% of accuracy, whereas for age, the accuracy decreases, but it increases back again when you separate the classes of age a little more. So if you want to distinguish between a 30 years old and a 40 years old, that's a little hard. But if you want to distinguish between a 20-year-old and a 50 years old, that becomes easier. As you can imagine, is quite natural. Also, another source of temporal data could be, for example, an EEG. We did this, actually, it's part of a very big project, learning from the EEG signal. In what case? As I'm referring to the physiology domain, that means that we are not checking for diseases, but we are trying to understand the brain processes. For example, not all of them, of course. In this case, in this experiment, it's an experiment about neurostatics. That is the study of how much you like what you see. And you can do this with EEG, for example, not only with EEG, transforming the signal. You can see all of the caps is a different source of variables. It's not just one variable, because there are many frequencies on each one of them. So you got a very, very tall tower of variables, of time-varying variables, from which you can try to learn a process. For example, a label: I like it, I don't like it, as the subject has expressed it. In our experiment, it was subject looking at artwork, and then at the end of the experiment, they said, okay, I liked the picture number 1, 3, and 6, but I didn't like the picture number 2, 8, and so on. Point is, was that written, or the question is, was that written in EEG? Spoiler alert, we have about 70 to 73% of accuracy, everything for in cross-validation, which is not that much. But again, you're trying to understand something very complex in the brain. Again, physiology. If you attach wearable to a human body, like everyone already has, even if they don't know it, like for example in your phones, you can use the accelerometer, dynamometer to understand what they're doing. If they're walking, if they fell, if they are sitting, if they're running, or if they just stand. This can be useful for some situation. In this case, a small company based in Ferrara, it's an international company, but it is based in Ferrara, wanted to proof concept the idea of being able exactly to identify the kind of activity, for example, in police forces, when they are on action, they cannot communicate, but you want to know if one of them has been hit, or maybe it's just he fell, or they're running without them telling, because they may not be able to talk, to speak, or whatever. In the case of a fall, actually our system is able to detect it in basically real time if a fall has taken place. Again, eye tracking. Eye tracking is the correspondent of EEG what it does is study the movement of your eye. In the same experiment of neurostatics that I mentioned before, some of the subjects were also wearing an eye tracker device. It's called Pupil, and what you can do is to take trace of your gaze in a target area. What is a gaze if not XY coordinates that change over time? Again, a time series. So remember, my point is to show that all of this is a time series. So in general, physiology is one of the sources. Physiopathology is much more common, is the study of the bodily function when something is wrong, say for example during an hospitalization. And then sensor and tests, they do produce time-varying signal, like the amount of temperature, pressure, or whatever you want to measure. They again change over time. It may be a different scale. For example, in all the examples that I mentioned before, the scale is 1 minute, 2 minutes, 3 minutes, while here it can be hours or days or even more, depending on what you are measuring and for what purpose. But the point is that you can produce time-varying signals for diagnosis or monitoring, which is absolutely common. I'm just mentioning because they are all the variation of the same idea. And last example, text. There are at least 3 ways in which you can convert text into a time series. One of them is by looking at words and taking into account the linear order that you got in text, and by a careful labeling of what you are interested in, you can convert it into a time signal. Another way is to use embeddings. You know that in large language model, for example, everything is based on embedding. Every one of them can be, every word can be thought as a token, because a token is then mapped into a high-dimensional domain. Those are numbers that change over time. So again, you can see it as a time series, as a time series. And again, you can use the amount of information that voice carries on while the text is pronounced. You can use them all together, or you can use them separately for different purposes. Emotion recognition, all kind of semantical labeling that you want to extract from text, either pronounced or read, depending on the case. Among all of them, only the text case is still, a project in our lab. We didn't actually do anything yet. We just published just a position paper that says, okay, you can do something like this, but we have no results yet. Everything else, as I said, corresponds to something that we actually did, and in most of the cases corresponds to industry that actually sign contracts with our department and our lab for us to solve their problem. Now, as I was saying at the beginning, all of these can be thought of as the same problem, and because they can be thought, in order to justify this claim, I have to say something about what I mean by logical learning from time series. So my problem is that I want to give meaning to this sentence. So the sentence is my temporal dataset satisfies a formula, and now I'm asking myself, how can I give meaning to this? And what we can find is that in order to do that, you have to give meaning to the sentence, the single time series satisfies a formula for each one of the time series of your dataset. This looks like a model checking problem, but now we have to understand what do I mean by what it is that I'm model checking, because the time series is not a logical model unless we convert it into one. So one thing that has been done, it's very popular, and probably at least half or maybe more than half of the logical learning from time series that has been done in the past is by using propositional logic. How can you do this? Take the entire time series, apply a feature extraction function, whatever that is, mean, maximum, minimum, number of peaks. You can have a whole dictionary of that, and actually in learning that is called feature extraction. Most of the learning literature is about what feature is the right one that contains the information that you want. But assuming that you have found out which features are interesting for you, then your time series can be converted into a propositional model. So your question, does the time series satisfy a formula, becomes, does this propositional model satisfy the formula? Well, how can you do this? By applying your feature to every variable, and then, for example, comparing the value with some constant. Now, what you can say is that this is not the only way to have a propositional vocabulary. I agree with you, but it is the way that has been more common so far. And if you look into a little bit into explainability and interpretability of models, then the more you complicate your propositional ladder, the less interpretable is the model you obtain, even if it is symbolical. So you want to keep that complexity down and still be able to learn something. Now, if you think of this, actually, all the time series, for example, classification system, are basically instances of this problem, because whenever you use, for example, an autoregressive method that looks into the past 5 values in order to predict the next one. Basically what you're doing is extracting feature that, you can do this in a continuous way, or you can do it in the discrete way. But in the end, what you're doing is that you are converting your time series into a propositional model. Is this the best way to, yes?
Do you need to apply the same feature structure function to each variable?
Absolutely not.
So it could
you
be
can,
different there.
Yes, it could be completely different.
Because if one of k, then you could have.
You can have
one
different ones. That of course depends on the case. If you're say, take one of the example before, voice that have different frequencies. Every variable is a frequency. Then it makes sense to apply the same features because they have the same nature. But take another one when you have gas output and energy or vibration, then of course the features are different. Okay. It makes sense, yes. So the question was, is this the best way to do it? No, it is not the best way. The answer is no, it is not the best way, but it has been the most common way. What is a better way to do it? A better way to do it is, okay, this is a time variable signal. So you take your favorite temporal logic, like LTL, or signal temporal logic, which is a variant of LTL with metric components and interpret over reals. And you can convert your time series directly without applying any function by just looking at the value and then discretizing those values. Say your value is higher than that or lower than that. So you're de facto converting one time series into an LTL or an STL model by simply labeling those propositional letters. So what you do is you take your temporal data set and you get a bunch of LTL models from which you want to learn something, from which you want to learn a formula. So basically, this is how it looks. And once again, is this the best way to do this? Well, if you think about it, what we did on the one side was to take into account the entire time series in the first method, so to say, of a bunch of methods. But you did extract some information from the value. You didn't just take the value as they were, because, as we were discussing a minute ago, you apply a function that may or may not unlock some hidden value in the information. In the second case, you forget about extracting this hidden information, but you take into account the relative position of what happens. And now, if you can put them together, that would be absolutely, the best idea. And it turns out that if you just take an interval temporal logic, not the kind of interval temporal logic in which there is no relationship between what happens on an interval and what happens on the inner interval or overlapping interval, because you want the most general setting. And you realize the easiest observation of all, that every segment of a time series is a time series on its own. So if that is the case, then every feature that you applied in the first case, you can apply to every interval. And besides having the same information that you had in the propositional case, now you keep that information, but you also keep their relative order. So basically, you convert one series into an interval temporal model. Does that convince you? Okay, so you can't be too picky about the quality of the not the quality, but the property of the logic itself, because in real cases you want to mix up what happens over an interval or with what happens on a single point with what happens in the entire time series. So if you really wanted to do this in a very general way, you shouldn't be using a pure, very natural language such as classic HS. You can mix it up with point-based intervals. You can mix it up with other operators. We are not interested in this case about deduction. So we don't care whether or not the logic becomes undecidable or very hard to reason about. We will care about that in the future, but not right now. In the real cases, what we did was to use pure interval temporal logic, and to be honest, sometimes the formula that you extract do make sense, and you can actually, and some other times they look a little strange, and we should look a little further into them in order to extract knowledge. And of course, you can do this. All together. You can extract propositional and point-based interval information, and point-based in temporal information or interval-based temporal information in order to understand what is the best way. But everything then boils down to the fact that giving meaning to the fact that to the question whether or not your temporal data set satisfies a formula is a function of the meaning that you give to the every single individual question. So a learning problem is a set of model checking problems, and if it is a set of model checking problems, what you have to do is to combine the result. But how can you combine them, and to what purpose? So of course you can convert your time series into a set of models, but then you have to combine the result all together in order to answer your original question. And this is basically another way to say that this becomes a learning problem, and because the learning problem has specific purposes, that will give you specific constraints on the formula you want to extract. It's not just about extracting one formula, you want to extract the best formula that does something. And now what I want to do in the third part is to go over the possible learning question that you may want to ask on your temporal data set, and see whether or not you can put them under the same title. Let's see if we can do this by focusing on learning. So, what is learning from multivariate time series? Well, of course, learning comes in many flavors. Symbolic learns comes in three popular flavors. Of course, there are other variations of other variants of learning, but in my experience, these are the most common ones. You can ask a question with your data set being labeled by 2 or more classes. That would be a supervised problem. You can ask your question your data set is labeled by exactly one class, which is not the same as saying there is no class. I will dig into this in a moment. And you can ask the question with no class at all. Of course, the fact that the problem is supervised or one class or unsupervised depends on how you use the class. Of course, your dataset may be already labeled, and then you can choose to ignore the label to solve a different problem, or if you want to solve a supervised problem, then in that case you need the label. You cannot avoid it. But what does exactly mean? Well, in supervised problem, that's very popular, everyone knows it, is basically learning the differences between classes, so learning a concept. In the old literature, this is called concept learning, and it is basically the same idea. What would you like from your formula when it is when you want to solve a supervised problem? Well, you want it to be minimal in size and as accurate as it can be. Minimal in size because this is the logical way to define, to avoid overfitting. The less you say about a bunch of time series that do classify them in an accurate way, the more general is the knowledge that you've learned. So it is a minimization problem. Two objectives actually. On the one side you want to minimize the formula, on the other side you want to increase your accuracy. Your accuracy can be measured as you want, in your cross-validation, with a test, or even in full training. Sometimes it does make sense, not many. What does it mean to learn with one class? Well, it means that everything is a positive example. Now, this has resemblance to automata learning, for example, and it's a different way to to look into this, although you cannot convert everything into automata learning because there are no automata for each one of the logics that you may be interested in. For some of them there are, for some of them there are not. But single classification means describing an entire data set and extract the essential idea. Everything you look into is a positive example of what you wanna extract. And the question is, how can I describe it? So again, what you want is your file should be minimal in size, but it should be subject to some constraint that makes it non-trivial. Right? You can say true about every model, and you get away with it. It is satisfied by all time series in the dataset, but you didn't say anything. So there are ways to syntactically and semantically constrain your formula not to be trivial, which makes the problem actually interesting. What is learning from a data set with no class? Well, with no class, or in which I am not interested into the class, well, this is unsupervised learning. And unsupervised learning means, or another way to call it, it's clustering. Now, for whoever has worked with data science and looks at the word clustering, immediately thinks about points that do cluster themselves in a bidimensional domain, and as I see a cluster there, I see a cluster there. How can I see it logically? Well, what is a cluster if not a subset of your instances that behave the same way, so they satisfy pretty much the same formula in such a way that those formula are not satisfied by the other cluster. So there is a way to logically define clustering. Your phi, your conjunction of phis, if you will, should be maximal in size, because the more thing you say about the cluster that is not true about the other cluster, it's better in this sense, and satisfied by the maximal time, but not all of them. This is a little misleading. What I meant to say is satisfied in such a way that it clearly defines the cluster. In your cluster, all of them should satisfy, but no one of the other cluster should satisfy them, and subject to specific syntactic constraint. What is the typical syntactic constraint in unsupervised learning? Well, they usually look like rules, because what you're extracting is association rules. Now, all of these can then be extracted, or how can you make it emerge from a data set? Well, in many different ways, but those many different ways, they boil down to a couple of essentially different ones. You can extract them as decision trees. A decision tree can be immediately turned into a logic formula. If you're thinking that right now only propositional decision tree exists, well, I partially agree. We've been studying in the past year non-propositional decision tree. We're not the only ones. There's a group from Trieste who does pretty much the same thing in STL. So the idea of extracting a decision tree that then you convert into a formula which is not a propositional formula, it's already out there. You can extract it as a decision list, which is the first cousin of a decision tree, although the underlying optimization problem is slightly different. Instead of divide and conquer, it's called separate and conquer. It's also information guided. It looks similar, and again, these are all statistical. The value of this is all statistical. So in some cases, proceeding in one way is better than proceeding in the other way. You can also extract this as a direct logical formula with deterministic method that build the formula bottom up in order to satisfy your constraint. And this is basically it. I mean, and of course, as I mentioned before, and I should have reviewed these approaches too. You can learn automata instead of formula, We got a lot bunch of literature about learning automata, but they only cover part of what we say. And I may be wrong here, but I think that no one tried to use automata learning algorithm to classify a set of time series. I have to look into that, but I don't think this is very common. So all in all, what you can say is that the temporal learning problem consists of extracting a logical formula from your data set. So if you put all these together, what you do is that you have a logical temporal learning problem. Is the problem that given a temporal data set, you want a formula that optimizes something, one of the things that we have mentioned before. And of course, this may look a little too abstract to be of any practical use, but as I mentioned at the beginning, we actually did this in the same way, in this way. And a good work would be, comparing. We didn't do that yet. Comparing the different approaches only from the logical point of view to see which one behaves better from the practical side and looks better from the interpretation side. So that would be something that we wanna look at. As I said, of course we're not the only one who do this. Many people does that, and the question is what combination are already known, and how hard is to perform such a learning. Now, some of these combinations are very natural, and it turns out they're not all that. Why? Well, probably because nobody just looked at the problem in the same way. I didn't do anything just by I just read the problem in a different way. For propositional logic, we all know that classical decision trees and decision lists are NP. Learning them is an NP complete problem. This is known for 40 years. One class I have never seen defined before. I guess it's probably trivial, and it's certainly in NP. And unsupervised learning in propositional logic means classical association rules. If that and that and that happens, then that happens. You can see it as a formula. Actually, what you learn is the head of the rule, not the rule as an implication. It's not a logical implication, but you need to learn the head of the rule. In LTL is partially known. There's a work. There's a work. It's relatively recent that looks into LTL, but now I have to stop a second and mention that on the vertical component of this table, I should have added all the possible variants that you can have in the same logic. One thing is learning an LTL formula. Another thing is learning an LTL formula of that shape, using only X, using only F, using only since, using only until, or other type of constraints. This has been studied in the LTL case, specifically for supervised and one class, but not for unsupervised, as I'm aware of. I mean, I may be wrong. And in terms of interval temporal logic, well, in this case, we are the only one doing it. So we have partial results for supervised, no result at all for one class because we have never actually looked into this problem. And we are publishing right at the moment a couple of attempts of learning association rule in interval temporal logic from temporal dataset. What we did was to generalize to the model case the two basic algorithms a priori from one side and FP growth on the other side, looking into the practical complexity and whether or not we can learn interesting stuff. In this example, which is curiously enough not one of the ones I mentioned at the beginning, we learn rules from this data set of people doing hand signs in the airport, whether or not you can, and the question of whether or not you can identify the hand sign being done. This looks like a supervised problem. We rephrase it as an unsupervised problem by learning rules from the partial data set of one class and then comparing how these rules hold in the other one, and then it turns out that if you carefully craft the propositional letters, that is the function that you apply to your intervals, then you can learn immediately intelligible rules that describe exactly what's happening there. And this data set has been around forever. It's a toy data set that everyone works. And if you look into the entire literature published on that data set, not a single one says anything about what does it mean for the people to do like this in order to stop a plane and say, okay, you are there. What does it mean logically? How can you describe in your logical language that specific movement? That is, I mean, to me, it looks interesting. As a final comment, and I think I'm already there. We should mention that these different ways to learn formulas should be crossed with a different way, with the different algorithmic approaches. And that typically, algorithmic approaches can be deterministic or non-deterministic. We saw that the problems are essentially NPR. Therefore, you can approach them deterministically, but you have to be happy with formulas that do not optimize what you want to optimize. For example, a decision tree learned heuristically doesn't give you the smallest one. It gives you one that is small enough, but it's not the smallest possible one. Or non-deterministically in a bunch of different ways. One relatively common one, and to me, the one that makes more sense when you look at the problem in a non-deterministic way, is to use genetic algorithms or similar meta-heuristics that take your pieces of formula, combine them together with genetic programming, and then try to optimize the function that we mentioned before. A third way to do this, pretty common in some part of the literature, is that you start with formulas that already have a fixed shape, and then what you learn is the parameters. Say, for example, the specific value cutoff values, or similar small parameters, but you don't let the formula move too much in the search studies. How can we do this in the same framework? Well, it turns out there is no framework in which you can solve this problem all together and play with them all together. So we built one. This is called the Sole project, and it's completely open source in Julia language. Julia, Edward mentioned yesterday, is a not very common programming language, but it is, it's a product of the Alan Turing Institute. So there's very serious people working into this. It is mainly for data science, but it is extremely efficient, and it is extremely efficient and has incredible parallelization features. So what we did is to build a framework that put together the two sides of this coin. On the one side, you can define your logic. Say, for example, one of the one I mentioned, and on the other side, you can twitch your data. In our case, it would be temporal data, but of course we didn't work in temporal data only. We also work in spatial data, for example, and you twitch it so that your data set becomes a set of models, and then you put these two things together by solving a model checking problem, as we mentioned before. If you want to learn a decision tree, well, you need a decision tree that is able to learn model formulas, and we're working into it. If you want to learn a set of association rule, you need association rule extraction algorithm like the one I mentioned before. We didn't work in the one-class problem yet, because we found out its existence only recently. So we didn't start working on it. But on the other side, what you can do is manipulate your formula. we are working right now on a general deduction system without claiming termination, of course, because we work just as well with decidable logic and with undecidable logic, and logic we don't know if they're decidable or not. But you can still have, some incomplete tableau system in this case, pretty general actually. You can put them, you can put in almost all of the logics that I mentioned, and of course, if you're lucky enough, your deduction will terminate. Why are you interested in deduction? Well, there are a number of problems that you can solve by mixing together the classical approach and the modern approach. One of them is minimization. If you want, if you're happy enough with your non-optimal learning from, let's say, non-optimal decision tree learning, and from that you come up with your pretty large formula. It is short, but it is a little too large. And then you ask your system to minimize it. Now, minimization is a general problem in logic. You can define you can define almost in a general way. And it turns out that every time you try to approach this problem, you have to solve a satisfiability problem hidden under the minimization. So we have a deduction system that does that. We are at the verge of putting everything together. The code is extremely complex, and there is, in my lab, there are many people working on this at different capacities. Bachelor students, master students, PhD students. So we try to work as a software house. We're not a software house, of course, but we try to work in the same way by releasing code that it is, the highest standard quality possible. And we do go to the Julia conference every year just to present pieces of the framework. Concluding, what we are seeing basically is that temporal and dataset and temporal learning is ubiquitous it pops up everywhere in your everyday reality. And of course, learning logic from data is like David against Goliath. Why? Because everyone else wants to learn sub-symbolic models. Everyone else wants to learn sub-symbolic models. But in the real world, data scarce. We are talking about, everyone knows that we are living in the world of data. We're not living in the world of data. Why? Because in many practical problems, the data are really, really scarce. Can you imagine how hard it was to have 200 subjects wearing a pupil, device, and having them looking at 19 different pictures for over 6 months, in order to work in an ecological system, this system that recreates the reality. It's not lab condition; it's ecological system. Many times, data are really scarce, and if you want to look, if you want to take the sub-symbolic approach, you always need a bunch, 1,000 and millions of instances. And the real world is explanation hungry. I mean, everyone wants the system that classifies, but then everyone asks why it does classify that way. And so you got the entire literature of explainability of the systems that are already black box. But as one author said, and it's not me of course, why learning something that it is black box and then try to explain if you can learn from the same data the explanation already. So that is basically my point. Thank you.
We can take some questions for the next 5 minutes. Yes, please.
First of all, thank you very much, because thanks to you, I've learned a lot about learning.
Oh.
So my question is more about the preliminary part of your talk about
Yes, please.
time series in
Where time series are, okay.
I was thinking that you have problems in which you have more discrete time series and problems in which you have more continuous data sets. And I was just wondering, you have problems in which the time series are inherently, naturally discrete. For instance, in some environment, when you cross doors, you have the signals of when you cross doors. And then you have the type of problems you present here that are, I suspect there are problems in which you have shifts in some values in the continuous signals and you try to extract them, I don't know. Or maybe you have problems in which it is really very, very continuous. So how your approach would fit these different...
What is the question that you are asking here? Is it the question, well, how can, say, what is the question you're asking? I mean, let's say you want to classify something. Whatever it is, whatever the answer is, it will be discrete in nature. So, even if the time series is continuous in nature, you need to describe, and everything has a sampling rate.
Yeah.
So it is actually discrete. I mean, the moment you digitalize an information, it becomes discrete. So basically there is no difference. The only difference is the scale. Sometimes you got milliseconds, sometimes you got days. So basically there is no difference in between. And if you can see, all these examples are all continuous, except maybe the text one, which is very unnatural. But I really challenge you to think about text in a time series way. It's an interesting idea. We want to really look into this how much you can learn. But to answer your question, to me everything is discrete.
The classical issues with when you are dealing with time series, and I was curious about whether you face this kind of issue. The first one is you have to manage time series having different times, different intervals, either regular or irregular, and you have to deal with data acquired at different sampling rate or something similar. Did you manage it? And the other stuff is, how do you deal with the null values? Many time series have some missing data somewhere, and that's an issue when you want to discover something.
It is an issue. First question, in all these examples, these are designed so to have the same sampling rate. It is not to say I don't want to deal with them. We just didn't deal with them yet. I think it could be a problem, and you mentioned it as a classical problem, and I will answer as a classical answer. Use the sampling, the most, the minimal sampling rate that has the most. But I'm not saying this is a solution that works in every case.
Practically, it is not feasible.
All right. The second one, it's interesting because if you are happy with dealing with a property, say for example of an interval, then you can deal with the missing value without having to impose it. If you want to look into how many peaks you can deal with the missing data, and statistically your data won't change very much because you are already abstracting over the property. But again, both problems, you say they're classical, we didn't really found them so often, so maybe there is a source of data that I don't know, and you should tell him, okay, these data have this problem, and we try to deal with them.
May I add a small question? Yes. Just about terminology, because when I saw your first slide, I was thinking from the database context, instead of formula, a query, and instead of learning, data mining.
Yes.
What are the connections, or did you consider also this kind of contributions?
I didn't consider it, but as we speak, and we spoke yesterday, I think these are the two sides of the same coin. It is, I completely agree. The temporal dataset is a database in a sense. The formula is a query. For that, I completely agree. If the problems are exactly the same, I know you deal with specific problems. They probably are not covered by these cases, and we probably should try to look a little more in that.
Thank you.
Thank you. A short one.
The question is short. I think there are two guests in your presentation. One you mentioned one, which was neural nets. The other one is large language models. I mean, you can do something also with these tools with respect to learning logical formulas and so on and so forth.
Well, the first question is easy, because from the last one, it looks like I don't want to look into them. I do want to look into them. Say, for example, to use them as a feature extraction. If you have a feature extracted from, we did this in a paper in Information and Computation published this year. Take, for example, voice, and you know that there is a neural network that identifies speeches and peculiarities that cannot be easily described as a function. Forget about it. Forget about it works. Apply it. That's a new feature, and also over an interval. And you are back there here. Your formula will have propositional letter that talk funny, but it will work. You see. So this is one way to do neurosymbolic, if that is. And the second question was about large language model. Well, we are ages away from that, but if you really look into how a large language model is designed, there are two components that are always there. First, the embedding. Second, the idea of predicting the next token. This is a large language model. You can define predicting the next token as a supervised problem. If you wanna, what is the supervision there? Well, of course, you've got many classes, not just one of them, and the data is the context. So whatever happens before. So you can define it in this way. Did we do it? No. Does it have hope to work? I have no idea. But I want to look into it because I'm guessing that some of the property of text can be described by logical formulas if you find the correct logic, which is not the same as solving the Chomsky problem of logically defining a language. It's a completely different idea. Is that whatever happened in the text before, described in this way, gives you information on whatever happens in the next one. Our purpose would be to have a system that works a little bit like that. Of course, you need the power, to learn that. And if you can only do a tiny fraction of that, you had uncovered something that right now is in the hand of some hidden function that you have no clue about.